So we're going to spend the rest of the semester talking about a couple different abstractions that are in the Haskell standard library that are super practical. People use all the time for all sorts of things. We're going to, I hope we'll use it to build a really elegant way to build parsers in Haskell. We'll see ways to maybe I'll show some ways to create animations. Maybe we'll think about ways to generate random numbers. And all of those things are going to use like the same couple concepts. So, before we get to that, we need to take a little detour to talk about something called kinds. So, of course you know that every value in Haskell has a type. Hopefully you know that by now. And it turns out every type in Haskell has kind. Okay, so kind is like the type of types. And before you ask, yes, sometimes people talk about, the next level up is called sorts. After that, there's not like specific words that people use, but you can end up with like a tower of like infinitely many things. Each one is a type of the group. We're not going to talk about that. In Haskell, all we need is kinds, and we're good. So, what are these? So, if we load up HCI, and actually, I'm going to so, what were we showing? Like plus, for example? Yeah. Yeah. So you're like, why is plus not in scope? Well, you have to read the error carefully. Type constructor or class plus. So plus is not a type. Right. So it says, I don't know, there's nothing named plus that's like a type kind of thing. So I can ask for the type of plus. Anything else, or anyone have any guesses as to what is going on? I'll give you one little clue. So I think Alexandria earlier said maybe integer. Map had a kind type. What if I just say maybe by itself? So that, it turns out, is type arrow type. Anything else you want to try?
I have one more.
Was that?
I have one more.
Okay.
A pair of int and a string.
Pair of int and string. Okay. Here's all the ones that are just type, and here's all the ones that are something else.
So the ones on top don't take anything as input. Bottom ones you have to give something like for list. I'm assuming they're asking type to type. You have to give. You can give like what is inside of the list.
Right. Yeah, so it's funny syntax, but it turns out you can write this. So like this thing just means list, but it's like list of what, right? So what do you, so what, if that's what's going on, like, you know, if I said like list of int, for example, what do you think, what kind do you think that would be? I think we just say type, right? Yeah. So Garrett is exactly right. What this has to do with is, like all the things up here, another term for these is, we'll call them concrete types. And they actually have, there are values of these types. So for example, you know, like 3 has type int. Right, all these types here that we listed, you could come up with an actual value that has that type. Like, you know, just 3 has type maybe integer. The list 4, 5, 6 has type list of int. A pair of, you know, 3 comma hello, that has type pair of int and string. These things down here, right, these don't actually have values. They are expecting, you know, well, I'll say one or more types as arguments, right? So like, it doesn't make sense to say, you know, that something has type maybe. It's like, maybe what? You can't just say this has type maybe. Right, maybe we say that informally if we kind of don't care what the value type is, or the type of the thing inside the maybe. We'd say, oh, it's a maybe type. But literally, you can't say like something is maybe. You have to say maybe int, or maybe char, or even maybe a if it's polymorphic. But you have to put something, right? And hopefully this is clear. But why do map and either? Why are they type arrow type? So they're just like type arrow type. Sam?
So it doesn't use values.
Right, yeah, so map you give it two types, the type of the things that can go on the left and the type of things that go on the right. So it actually corresponds pretty closely to, how function types and applying functions works on values, right? If I have a function f that has type, int arrow int, that means I could write f3 and that now has type int. Because I put in the int argument that I wanted and it's going to give me an int as output. Right? Maybe is type arrow type. That means if I apply it to a type, if I write maybe int, that whole thing, now I get a type. So they really are, these really are functions taking types as inputs and returning types as outputs. They really are functions that just like kind of work on the little types of values. Okay. And I'll just say, in general, type is a kind, and if K1 and K2 are kinds, then K1 arrow K2 is a kind. So actually, let's see, let me come up with one. Don't worry about what this is. I was trying to come up with an example showing that not all things have a kind that's just like type, arrow type, arrow type, arrow type, arrow type. So this thing actually takes 3 arguments. The first is a type. The second is a type arrow type thing. So for example, maybe, right? And then the third is a type. We're not going to talk about what this, oh, we might talk about it at some point. I don't know, but I don't know if we're going to get there. It doesn't matter what it is, but the point is, there are like more complex and abstract things that kind of take, just in the same way we have higher order functions that take functions as arguments, right? There's like, this is like a higher order type that takes like not just a concrete type as an argument, but like a typed function as an argument. Okay, cool. Any questions? So, I guess the last thing I'll say is, Haskell does kind checking in the same way it does type checking. So, for example, we can, let's see, if we try to make a function f that takes an int and gives a maybe, int string, right? F3 equals nothing. There's not really anything wrong with the definition of f, but the type doesn't make sense because maybe, you can't apply maybe to 2 different types, right? It takes a single type. And if we try to load this and see what kind of error we get, I guess that has to go. Yeah, see, it says, I expect, okay, so the other thing you have to know is that originally in Haskell, like, instead of writing the word type, it used the symbol star. So star means the same thing as type. So let's say note star means the same as type. And for various reasons, Haskell is kind of trying to move away from using star to using type. But that's why I had to like enable that extension because like star is still the default. Because tons of code uses it, and so it would kind of break a lot of things. But I just thought type was clear, to introduce the idea. But if you see star like this, you can just think type, right? So this makes sense now, right? It says, hey, I expected kind star arrow star because you had a thing that was applied to string, right? So that if you're applying something to string, then that something had better be, take a type as argument and return a type output. I expected that, but maybe int has kind star. So like the kinds don't match. So this is actually a kind mismatch error. And we could also, we could get a similar kind of thing if we said like, if we just tried to do int arrow maybe. This might be a more plausible error. If someone didn't really understand that maybe had to be applied to a type, they're just like, oh, I did maybe. Right? It says, hey, I was expecting one more argument to maybe. Right? I was expecting a type, like that is a type of, something of kind star. But maybe has kind star and arrow star. So maybe we want to give it another argument. Checking errors. Just slow that down. Okay. Cool. So, why did we need to do this? We needed to do this because we're going to learn about some ways to abstract over certain kinds of things like list or maybe, either, all these kinds of things that, we need to be able to talk about, we need to be able to write down the kind of something because we're not just only going to be working with things that are concrete types. Okay, so, all right. So let's think about mapping. So, for example, we all know and love the map function on lists. Right, I'll just write it out here, but we all write map of empty is empty list, map f of x cons x's is fx cons map f x spec. Yeah, of course it's going to yell at me because there's already something being mapped defined, but that's not. If we define like binary trees, so tree A is like empty or node tree A. Okay. Alright, we can write a map tree function, which again takes A arrow B, tree A, and turns a tree B. Now tree, well, if we give it an empty tree, we get empty. If we give it a node left, x right, we get a node, map tree f L. We apply f to x, and then we map tree f on. We also had like on a homework, on one of the modules we had like this rows type, which is a node. Like this. So call it R node. And we could say map rows. I'm not going to take up the whole thing of this, but well, why not? All right. So we say map rows f of R node x R's is what we apply. We get an R node. We apply f to x, and then we need to map the function on each of the child rows trees. So we say like map. Right. So obviously, and we've thought about this before, like these are all they're doing something very similar, right? They all have pretty similar types. And they're all embodying this idea of, I've got a thing full of A's, and I want to take a function from A to B and like apply it to all the A's and turn them all into B's, and then I get a thing full of B's. At this point, we might wonder, like, hey, something, like, can we kind of like, abstract over all these things and just write like one map function to rule them all, right? So can we say something like, you know, I'll call it Gmap for general map. That maps on anything. Well, what would its type be? So, I mean, we can look at these three types, these examples that we have, right? We can say, well, they're all going to start with, you know, some A to B function. The part that's different, right, is it all has like something A to something B. The something is the part that's different, right? That's the only part that's different. So here I have tree, here I have rows, here I have list. And actually, right, even though list has a special built-in syntax, as we saw, like you can actually write just square brackets like that to mean like just a list type that takes a type as an argument. You can actually write it like this. It looks a little odd, but it's like list applied to A. But it just makes it look more similar to these. So maybe we'll just say, all right, well, I'll just say, you know, it can be anything, right? So it doesn't have to be tree or row specifically. I'll just say, you know, F. Or maybe T for thing. But, right? So this is kind of what I want. So then, how would I implement this? I say, well, I have my function F, I have my thing T, which is full of A's. I'm going to give a thing full of B's. How would I do this? Let me ask you a different question. If I were, you know, like when we were implementing map rows, for example, you know, if I didn't have all this code here, if I just said map rows f r equals underscore, right? What would be kind of the next step we would take at that point as we were trying to implement like that? That's too big. Let me make it more. So here's what we ended up with, right? I'm just trying to like, you know, think back and kind of imagine our thought process as we went about implementing this in the first place, right? So we might start by saying, okay, map rows, it takes a function, I'm going to call that f, it takes a rows A, I'm going to call that r, and I have to give back a rows B, right? What will be the very next thing we might do at this point? Tim?
You need to take one of the A's out or
Take one of the A's out. Yeah, how do I do that though?
by pattern match.
Right, I pattern match on it. So I said, well, I need a pattern match on this R. And so I would replace it with this pattern. I'd say, well, okay, a rows A has to look like this, and then I can make some more progress. I say, okay, well, I got this X, I take my F to it, blah, 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 right? Same thing here, right? So in map tree, I said, all right, I need to pattern match on the tree. And so I say, well, it's either empty or it's a node, and I do those two cases, right? So the point is that, you know, at this point, like the next thing we would need to do is pattern match on T, right? However, we can't. We're stuck because we don't know what this type T is, right? What type it is depends, like that's what determines what constructors it has and how we can pattern match on it, right? That's why we only needed one case for our node because it only has one constructor, but we needed, you know, two cases for tree and two cases for map for a list. So we can't actually write this. It really does depend on what T is. It's going to work, even though it's very similar. How it works is going to depend on what that type is, right? We're stuck. we say, all right, I've got this common pattern. I want to have like a function that will work on sort of a wide range of types, but it's got to work in a different way for each type. That's exactly the situation in which we want a type class. Right? That's what a type class gives us. It says you can define these functions. They're going to work on anything that's an instance of this type, but depending what actual type it is, they'll work in it. You can implement them in a different way. But it still is nice that we can just use that one function, and it'll figure out which implementation to use based on what type we use on, right? Because right now, if I have a list, I have to call map. If I have a tree, I have to call map tree. If I have a rows, I have to call map rows. Wouldn't it be nice if we could just say map, and Haskell would just figure out which way to map, depending on what thing we're mapping on. So idea is a type class. Okay. So we're going to call it Mappy. Of course, this exists in the Stems library. It's not called Mappy. It's called something else. I'll tell you what in a minute. But we're going to make our own version of it. So the thing that we need to abstract over, the thing that's going to be mappy, is this T, right? That's the part that's actually changing. And this is why we need to talk about kinds, because like what kind is T here? Like in this Gmap thing, what kind is T? What do you think? Type to type, right. It has to be type to type because anytime you have something on the left or right on a function arrow, that has to be a type. You can't say like maybe arrow something. That doesn't make any sense. So A and B are definitely have kind type. So like A could be int, it could be maybe char, it could be list of string, but it can't be like maybe. And then TA, the whole thing has to be a type. And so, well, T, if we're applying it to a type and we're getting a type that outputs, so it has to be a type arrow type. So T could be something like list, or rows, or tree. Right? I guess we didn't talk about these, but like, of course, rows has, oh, look, it says here, rows has kind of type arrow type. Right? Tree also. And so, really, I have to turn on some, let's see. I think we have to import. If you want to use type, you have to import it from data.conf. Anyway, so this is not required. We could just say mappy t where, and it would figure out, just based on the way we use it, it would kind of infer that it has to have kind type arrow type. But it's nice to record it explicitly. For the same reason, it's nice to write down explicitly the types of our functions. Okay, and we want to say, well, I'll call this mappy. Okay, all right, T can be mappy if there's a function, which we'll also call mappy, which takes an A, B, and a TA, gives us a TB. Okay. And then, excuse me, we can say, instance mappy list, where mappy equals map. We can say instance mappy tree, where mappy equals map tree. that works. I can say Mappy plus 1 on a rows tree, so R node. Right. So Mappy doesn't care. It'll work on any of these things that are instances. Haskell will automatically figure out the right implementation to use. So this is nice for a couple reasons. One is that the simple reason that we just now no longer have to remember the names of a bunch of separate functions, right? You know, if I want to apply a function to everything in a rows tree, I don't have to remember that it's map rows or whatever. I can just say mapping. The other reason is that, and I don't know if we'll see examples of this today, but we'll see them later. We can now start to write functions that will work for any mappy thing, right? Instead of just like for a specific type. And that gives us some extra power. Any questions at this point? So, I'll tell you now, and then I'll reveal. In the standard library, what we've called Mappy is actually called Functor. And what we've called Mappy is called Fmap. I think the F stands for Functor, like Functor map. And you might wonder, and some people do in fact argue this, that really it should just be called map. And like the version that works on lists specifically should be called like LMAP or something. But it's just kind of historically that's the way it was named. You know, maybe beginners would be more confused if the type of map had some complicated thing about functor than it was just about list. That one I don't really buy because you can just tell them list map and not tell them about map. I don't know, but I don't think it's ever going to change. That's the way it's named. So.
Why would they go with Functor?
Why is it named Functor? So basically, it was an existing math concept that this is kind of an instance of, and which is called Functor. And so,
Does that only contain like all of the different math stuff that you're showing here? Like put a bunch of different ones, or does it contain other stuff as well?
oh, does that class contain other things? No. It's that, well, okay. It contains a couple other things just kind of for convenience, but nothing fundamental. I can show you actually the definition. No, it really is just, there's a lot of instances, but here's the definition right here. So here's Fmap, right? That's exactly, and it's using the letter F. F for functor instead of, we were using T, it doesn't really matter. It's the same thing. So A to B, FA to FB, and then it has this special version here. Actually, here, this is a nice exercise. Let's just see what it is. So let's see if we can write. So, and also, if you notice this thing that says minimal Fmap, really what that's saying is, to make an instance of this class, really all you have to do is implement Fmap. And if you implement Fmap, then this thing will get a default implementation in terms of Fmap. We haven't seen how to do that, but when you make a class, you can kind of say, oh, there should be these things. Oh, and by the way, here's a definition for this one in terms of the other one, so that if you don't want to define it, it'll just be defined in terms of the other one. The reason to have that is because for some particular Fs, there may be a way to implement this that's more efficient than the default one, and so it might be nice to actually give a specific implementation for both, which would be more efficient. But if you don't give an implementation for this, then it'll just use the default one, and it'll still work. So that's it. That's all that's in there. So really, it's just all about this Fmap thing. This is just for convenience. And just for fun, let's see. So this is an example of a generic thing we could implement for any functor, for any mappy thing. So using our version again, we can say like, so we can implement something of this type, but we'll say, look, we can do this as long as T is Mappy. So for any Mappy T, it's probably, oh no, it's just, for any type T which is Mappy, then we can make a function that has type A to TB to TA. Okay? And if you just, let's just stare at the type and think about what this could possibly mean. So it takes a value, like a single value of type A, and it takes a TB, which we could think of as like something full of B's, and then I want to get back a thing full of A's. What do you think this could possibly do? And if you want to, you can think about some concrete examples. You can make it slightly more concrete. If we think about T being like list, say. If I'm given a single A, and I have a list of B's, and I want to turn it into a list of A's, like how might I do that?
If you just replace every B, EB with that A.
Okay, so you're saying, let's just take all the B's and replace all of them with that one A.
Yes.
Okay. What do you all think? Would that work? Does that make sense? The other question is, could it, I agree, that would work. Could it possibly do anything other than that? Okay, well, I'll let you stew on it, but I'll tell you now. The answer is no. That's actually the only, even just looking at the type, because of parametricity, right? Remember this property that polymorphic things have to work kind of without knowing anything about the type, and they have to work in the same way no matter what types you put in. That's the only possible thing this could do. For one thing, it doesn't know anything about the type A. So the only place it could possibly get any values of type A is this one A that it's given, right? And so it can't, like, for one thing, it can't, replace the B's with like different A's, because there's only one A it knows about, and that's the only thing it could possibly use. The other thing you might wonder is like, well, if T was list specifically, I could just say, oh, I take an A and a list of B's, and I'm just going to return the empty list. Or I'm just going to, return a list that had just a singleton list with just that A in it. Maybe the list of B's had like 10, but I'm going to just return a singleton list. That would work for lists specifically, right? But also, this now has to work for any Mappy thing. It has to work for lists, it has to work for rows, for tree, right? And kind of the only thing we can do is apply some function to everything, every B in here. And so we kind of have to, it has to keep the same shape in some sense, right? So if it's a list, you have to get something with the same length. If it's a tree, you're going to get a tree with exactly the same shape. All you can do is kind of go over the whole tree and do something to every B. And the only thing we can do to every B is just replace it with this A, because that's the only A we know. So this replaces every B in a TB structure with a single A. So the way we would implement this, right, so I'm saying I'm given the A, I'm given the, we'll call it TB, right? So TB is this thing of type TB. And the only thing I can do, I can say Mappy, I want to map some function given a B, what A are we going to turn it into? And really, we just have the single A, so the only thing I can say here is ignore the B and just return that single A. You might wonder why this would be a useful thing to do. It's occasionally useful. For example, I'm trying to think of times that I've used this. Maybe you, well, no, okay, I won't say that example. Let's say you have a list of things and you don't actually, or maybe, yeah, you have a list of things, but then you want another list which has exactly the same length because you need them to like match up. But this other list that you need is just going to have, you know, all values at the same time. And of course, you're going to use that for something else, right? But it's important that these lists have the same length. An easy way to do that, so what you could do, right? You could like call length on the first list, and you know, find the length, and then say like replicate, you know, like make a certain number of copies of something, right? But you could also just say, oh, take that list and just use this operator and like replace everything in the list with this one line. There's other examples that we'll see when we look at other applications of this, but anyway. Yeah, sure.
So that makes a list with the same length, like hypothetically if we're using the list.
Yeah.
It would make those the same list, just with a different type, and it would have the same length with that list.
Yep. So let's hear. So if I said, right, so this is going to say, it's going to take this entire list and just replace every element in the list with hi. Right, oh, well, okay, right, of course it's, you know, let's name ours something else. Or if we had like, let's go back. Right, here we had our rows tree, right? So we could do the same thing here. We could say this. We get the same structure, the same tree structure, just every value in it is now high. Whatever. It's just an example of a function we can write that works for any map. Right? So now we just get this function for free. Anytime that we have something and we have a functor instance or a map, we can use that. So we've got a few minutes. Let's just do one more thing. And then we'll pick up on this later. So I want to start looking at more examples. Because it turns out there are tons of examples of types, things of kind type or type, that are functors, aka Mappy. And some that we haven't really thought about before. So here's the first one I want to think about. Instance, Mappy, maybe. So, well, we need to write something of this type, right? It takes A or a B, and maybe A, oops, and returns a maybe B, right? actually kind of a plugin for how someone can do that. But so if it's nothing, the only thing I can get back is nothing, right? Because I don't have a B. I don't even have an A, so I can't get a B. But it also makes sense, right? Because what we've seen is that Mappy in general, it preserves the structure of the thing, right? All it does is it goes through the structure and replaces every A with a B. It doesn't like change the structure. So if I start with a nothing, I shouldn't change what I have. I just have it. But if I have a just A, I'm going to get a just out. But I need to apply F to that A, and I also get a B, right? So just. Right? That makes sense? So this doesn't look that, there's not that much going on, right? But I bet you that all of you have written code like this before. You've probably written code that was like, you know, blah, 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 and you're like, oh, I'm going to call this function, you know, f of, you know, x, and that's going to give me a maybe. Or no, I have some x which is a maybe. Well, I'm going to call it that. And you're like, well, if it's a, you know, it's like, if it's a just, or if it's a nothing, then I'm just going to say nothing. Like, that means something failed, so I don't want to return anything. But if it's a just, you know, x, then I'm going to return just, you know, fx. You've probably actually written code like this. So for example, you know, like if you were working on the module where you had to do like the little type inference for Haskell. Like, well, let's look at the left side. Did that give me a type? It returns a maybe type, and if I got a nothing, then the whole thing failed and I give a nothing. But if it returned a just, then I need to do something to the thing that returned to like give the type that I actually want, right? But this is really just, right? I should say just. This is equivalent, right? You could also just say Fmap F. Right? So this instance is at the Functor instance for maybe, plus a few other things that we're going to learn about later. Really, like experienced Haskell programmers very rarely write explicit case expressions where they pattern match on nothing or just. Right? They use tools like Fmap to kind of do that pattern matching for them. There's other, I mean, maybe there's other ways you could do this. Maybe you don't return a, you know, a just in this case, but there's other tools than this. But, so that's kind of nice, right? This is kind of the idea. Like, if I have something that failed, then it should stay failed. But if it's successful, then here's a function I want to like do one more step of computation to, and that's kind of expressed by this. All right, next time we'll look at some other examples